This video is going to cover section 4.2, paired T procedures. And I'll do a couple of homework problems here. Now, our homework in section 4.2 is problems 9, 10, 11, 12, 13, and 14. I'm not going to do all the problems, but I'll do a few. Maybe I'll do two. We'll see how that goes. And if it goes pretty quick, we'll maybe do three. All right. We'll start with problem 9. It says climate change, part 1. Is there strong evidence for climate change? Let's consider a small scale example comparing how temperatures have changed in the US from 1968 to 2008. The daily high temperature reading on January 1st was collected in 1968 and 2008 for 51 randomly selected locations in the continental US. Then the difference between the two readings, temperature in 2008 minus temperature in 1968, was calculated for each of the 51 different locations. So the key idea here is we have a location in 1968, and we have the same location in 2008. And remember, the idea behind a paired T procedure is we have two samples of data. We have the data from 1968 and we have the data from 2008. But because there's a relationship in this data, it comes from the same location. This reading in 1968 came from the same location as this reading in 2008. And we are going to then, because we have this relationship, and it's up to us to see that relationship, it's up to us to see that these are not independent observations. They're related. They come from the same location. What we've said is we're going to calculate the difference in temperature between these. And the way the problem has identified the difference is it says we're going to take the temperature difference in the temperature in 2008 minus the temperature in 1968. And we did this for 51 locations. So N for us is 51, which means our degrees of freedom, which is N minus 1, is going to be 51 minus 1, or 50. Okay. The average of these 51 values was 1.1. So X bar for our differences was 1.1. And the standard deviation S for our differences was 4.9. Again, the key idea here is because we have a relationship between the data in 2008 and the data in 1968, that observation came from the same city or the same location, here minus here, 51 different cities or 51 different randomly selected locations. We are going to do this as a paired T procedure. So we calculated the difference. That gives me one sample, just one, because I just have all these differences. Again, we don't have the data. We just have the summary statistics. They told us on average, the difference in temperature was 1.1. On average, it was 1.1 degrees hotter in 2008 than it was in 1968. But our standard deviation is 4.9 degrees, right? 4.9 degrees. Part A says, is there a relationship between the observations collected in 1968 and 2008, or are the observations in the two groups independent? Explain. We've already done that, right? We finished that. I've been talking about, since we started this problem, that there is a relationship between these locations. This data is not independent. Part B says, write a hypothesis for the research in symbols and in words. So our hypothesis, our null hypothesis, is going to be that the average change in temperature has been 0, i.e., in words, the average difference in temperature between 2008 and 1968 is 0 degrees. And we have to write it in symbols and in words. H sub A, well, that's what we're trying to test. And is there strong evidence of climate change, right? That's the question. It says, let's consider a small scale example comparing how temperatures have changed. The daily high temperature reading was collected from 51 random select locations, and the difference between the two, is there a relationship? That's part A. Write a hypothesis for this research in symbols and in words. We're concerned about a change. We're not concerned about it getting hotter, where it would be warmer here versus here. Or we're not concerned about it getting cooler, where it'd be here versus here. We're concerned about both of those. So this is going to be a two-tailed test, right? The alternative hypothesis is the average difference in temperature between 2008 and 1968 has changed. We're not saying it's gotten hotter. We're not saying it's gotten cooler. We're saying there's been a change. So we would write that out. The average difference in temperature between 2008 and 1968 has changed. Okay. So part B said write the hypothesis in symbols and in words. We've done that. Part C says check the conditions required for this test. So part C says check the conditions. Well, what are the conditions that are required for this test? Well, we have a sample size greater than 30, right? Our sample size N is greater than 30. Our observations are independent because we have 51 independent locations. There's no relationship between these cities, so our observations are independent. And we need to know about the shape of our distribution, right? A shape of our data. They don't give us any information about that. They didn't give us a histogram to look at. They didn't give us a box plot. They didn't give us a stem and leaf graph. They didn't give us the data so we could build those things. So we're just going to have to, because we want to proceed and finish the problem, we're going to have to assume that the shape of the distribution is approximately normal. Now, it doesn't have to be approximately normal because our sample size is so much bigger than 30. We could have some problems with our data and still overcome those. It would still be okay to use our T procedures because our T procedures are robust. They're able to handle a glitch here and there. But those are our conditions. Part D says calculate the test statistic and find the T value. Now we know our test statistic T is equal to X bar minus our mu naught divided by S over the square root of N. So for us, that's going to be our X bar, which is 1.1, minus our hypothesized value for our differences. In this case, that's going to be 0, divided by S, which is 4.9, divided by the square root of our sample size, which is the square root of 51. So if we do some algebra here, that's 1.1 times the square root of 51 divided by 4.9. I have a calculator here with me. So if we do that math, we have 1.1 times the square root of 51 divided by 4.9. And we end up with a T statistic of 1.60. Okay, that's our T statistic. And then it told us to find our P value. Now, in the last homework assignment, we learned how to use the T distribution to find our P value. So I'm not going to go over that again in this video. If you need that, watch the video on section 4.1. Our degrees of freedom here is 50, right? Our degrees of freedom is 50. So I go down to the row that's 50 degrees of freedom. We're doing a two-tailed test, right? A two-tailed test. And I try to find the gap that would contain 1.60. 1.60, right? 1.60 turns out to be between So our p-value itself, because remember we look at the gap, our p-value turns out to be less than 0.2, but greater than 0.1 for our two-tailed test. The important thing then for us is that our p-value is greater than 0.05, which is our typical alpha value, our typical reject region. So since our p-value is greater than 0.05, we're going to fail to, well, we're just doing part D. Part D said find the p-value. Part E says, what do you conclude, right? Your author's walking us through the whole test piece by piece by piece. So part E says, what do you conclude? So we're going to conclude, since our p-value is greater than 0.05, we're going to fail to reject H naught, right? And it says, what do you conclude? Interpret your conclusion in the context of the problem. So we are going to say, we failed to reject H naught, which means we cannot reject the possibility that the change in temperature was 0. So we did not provide any evidence that it was getting warmer or cooler. We could not reject the possibility that the change in temperature was indeed 0. We failed to reject this outcome, and this outcome said the change is 0. Part F says, what type of error might we have made? Explaining the context of what the error means. Well, we don't know what kind of, we could have made a type 1 error, right? We could have made a type 1 error. Type 1 error, remember, if we go back and take a look, we could have made a type 1 error. Type 1 error, remember, says we rejected H naught when H naught was true. Well, we didn't do that, right? So we could have made a type 2 error is what it turns out. We could have failed to reject H naught when in reality we should have rejected H naught, right? That's the type of error we could have made. Explaining context what this error means. We failed to reject H naught. So we failed to reject the idea that there was a change, the possibility that there was a change in temperature, when in reality, maybe there was a change in temperature, right? That would be our type 2 error. Part G says, based on the results of this hypothesis test, would you expect a confidence interval for the average difference between the temperature measurements from 1968 and 2008 to include 0? And the answer to that is yes, we would expect a confidence interval to include 0, right? We would expect 0 to be present. Why would we expect 0 to be inside here? Because we failed to remove our possible values if we build a confidence interval. If we just real quickly off to the side here, we'll do it in purple. If we just real quickly built a 95% confidence interval, all right, we'll just throw one together really quickly here. We know, how does a confidence interval work? Well, it's X bar plus or minus our t statistic for a 95% confidence interval. So we would need to grab our t table again. Remember, we're at a degrees of freedom of 50, a 95% confidence interval. That means 5% in two tails. So I go across the two tails to 5%. That gives me 2.01 as my critical value. And then I have S, which was 4.9, divided by the square root of n, which is the square root of 51. And if we do that, we get 1.1, right? And if we do the math over here on our margin of error, we're going to get 2.01 2.01 times 4.9 divided by the square root of 51. And that gives us a margin of error of 1.38. Now, if we take 1.1 plus 1.38, we get 2.48 as our upper bound. But if we take 1.1 minus that, right, we're obviously going to get a negative number. If we take 1.1, span 0, zeros inside. All right, so that's how we do problem number 9. It walks us through the hypothesis test, start to finish, piece by piece, step by step. Now remember, our homework here is problems 9, 10, 11, 12, 13, 14. So that was problem 9. I'll do problem 12. Okay. I'll do a second one. We'll do problem 12. They're all going to be essentially the same, right? They're all essentially the same. It's paired key procedures. So I'll go ahead and do problem 12 as well. So use what we did here in problem 9 to work out problems 10 and 11, right? They should work out in a very similar manner. You should write out as many things as I wrote out when I did my problems. We're in a statistics class. We're in a university course. We're not trying to write the minimum amount. We're trying to write the necessary amount. All right. So let's see what problem 12 says. What does problem 12 say? Problem 12 says high school and beyond. We considered the difference between the reading and writing scores of a random sample of 200 students who took the high school and beyond survey. The mean and standard deviations. So here's what we have. We have 200 high school students. Remember, this is problem 12. So n is 200, which means my degrees of freedom is going to be 200 minus 1, or 199. Now, we do not have a row for 199 on our table, right? We do not have a row. If we look at our table here, we do not have a row for 199. We have a row for 200. We have a row for 150. But we do not have a row for 199. So we're going to use 150. That's the conservative approach. That will minimize our error. We always go to the next value down below our number. If our number is not there and we have 199, it's not there, even though 200 is really close. The reason your author put this problem in the book is to make sure that even though it's really close to 200, you don't use 200, you go down to 150. So we're going to use 150. It says we consider the difference between the reading and writing scores. So we have X bar, and this is the reading minus the writing score. And that turned out to be negative 0.545. And the standard deviation of this, that's reading minus writing, turned out to be 8.887. That's a huge span, right? That's a huge span. That's a standard deviation of 8, when our mean is only 0.5, negative. It says, as we continue to read, part A, construct a 95% confidence interval. So we know how to do that, right? Part A, a 95% confidence interval. We just did a confidence interval in the last problem. So we're going to have X bar plus or minus T star times S over the square root of N. And we know all these values. X bar is negative 0.545 plus or minus. Now, where do we go to get our T value, right? That's what this problem is really quizzing us on. It's making sure we know to go get the T value on row 150 and not row 200. Now, we want a 95% confidence interval. That's 5% in both tails. We're going to go to row 150. So that's going to be a T star of 1.98. Our standard deviation is 8.887. 0.887, and our sample size is 200. So that's going to give us negative 0.545 plus or minus, and then we can calculate our margin of error, right? And so if we grab our calculator here, our margin of error is 1.98 times 8.887 divided by the square root of 200, and we get 1.244 for our margin of error. Okay, and then we would just add and subtract those, and that would give us our confidence. Interpret this interval in context. We would say we are 95% confident that the average difference in reading score minus writing score, right? The average difference in reading score minus writing score for the students is going to be between the lower bound and the upper bound. It's so important that we write that out. We are 95% confident that the average difference between the reading score minus the writing score is between, and then whatever you get for your lower bound and whatever you get for your upper bound. Okay. Part C says, does this confidence interval provide convincing evidence that there is a real difference in the average scores? So see, the problem I worked on last time, we started with a hypothesis test and they had us do the confidence interval. And they said, well, what do you think? You know, 0 an opportunity to show up. It is that maybe it does, maybe it doesn't show up in the confidence interval. How do you feel about that? Well, we had failed to reject 0. So we expected it to be in. If we look at this, we have negative 0.5. So if we write down the confidence interval, right, if we actually write it down, we have 1.244 plus negative 0.545. That's going to be 0.699. And if we go the other way, we have negative 0.545 minus 1.244, and that's going to be negative 1.789. And look, this is negative, this is positive, 0 is inside our interval. So if we go back and look at part C, right? If we go back and look at part C and it says, does the confidence interval provide convincing evidence there is a real difference? Well, our null hypothesis, right? Our null hypothesis would have been mu equals 0. And that would be the differences. That would be our null hypothesis. And it says, is there a real difference? So our alternative hypothesis would have been the mean of the differences is not 0. Well, because 0 is inside this interval, it's a possible value. Our confidence interval says we're 95% confident the average difference is between here and here. One of those values is 0. So it makes sense then that given this is our null hypothesis, we would fail to reject this. Again, why would we fail to reject it? Because 0 is one of our possible answers. So the idea of the confidence interval and the hypothesis test, they support one another, right? They're not equivalent. No one's saying they're equivalent, but they support one another when it comes to their conclusions. All right, the rest of the paired problems look just like these. So use these as a basis to complete your homework on section 4.2.